So if P dollars are deposited in an account paying an annual interest rate R compounded or paid N times a year, then after T years the account would allow A dollars, would contain A dollars. So amount equals the principal times 1 plus the rate divided by the number of times it's compounded in a year, and then the times the time and that number of the years and the number of times it's compounded each year. So using that formula, and we'll remember that that formula is A equals P times 1 plus R over N raised to the T times N. Suppose we have $2,500 deposited in an account paying 6% interest per year, compounded semi-annually or twice per year. Using this formula, for A, find the amount in the account after T years with no withdrawals. So just let it sit there. So A equals the principal, $2,500 times 1 plus the interest rate as a decimal, so 600ths, divided by the number of times compounded a year, which is twice in this case, raised to the 10 years times 2, compounded twice a year. We need to find this equation then. And what I would truthfully do is grab my calculator and rounding that to the nearest dollar or nearest cent, I would come up with $4,515.28. So that's how much money would be in the account after 10 years with no withdrawals. B says how much interest was earned in that 10-year period. Well, that B answer then takes the interest or the total amount in the account and subtract the $2,500 started with, and we'll find that in that 10 years the account earned $2,015.28 interest. Goldberg must pay a lump sum of $15,000 in 8 years. What amount deposited today at 4.8% compounded annually will grow to that $15,000 in 8 years? Well, we're still using the same formula. A equals P times 1 plus R over N to the T times N. What amount deposited today? So it's the principal amount we don't know. We know that we want $15,000. That would equal principal times 1 plus, now this is compounded annually, so it's 1 plus 0.048 divided by 1 to the 8th. I want to solve for P. I find P equals 15,000 divided by 1 plus 48 hundredths to the 8th. I would grab my calculator again and round my answer to the nearest cent. Do make sure when you do the calculator you have 15,000 divided by this quantity, 1 plus 48,000 raised to the 8th. I would just round that in parentheses again before I put it in my calculator. And I'll find out that to get that 15,000, I need to have deposited $10,308.63. Now, the more often the interest is compounded in a given time period, the more interest will be earned. Surprisingly, there's a limit to the amount of interest, no matter how often it is compounded. Suppose $1 is deposited at 100% interest per year, compounded n times a year. Then the interest rate in decimal form is 1.00, and the interest rate period is 1 over n. According to the formula, with p equal to 1, the compound interest at the end of 1 year would be the compound amount at the end of 1 year, but a equals 1 plus 1 over n to the nth. Well, wait a minute. That looks vaguely familiar. Isn't that what we used to find e as n went to infinity? Well, there it is. If p dollars are deposited at a rate of interest of r compounded continually for t years, the compound amount of dollars on deposit is a equals p to the ERT. So here's a problem. Suppose $8,000 is deposited in an account paying 5% interest compounded continually for 6 years. Find the total amount on deposit at the end of that 6 years. So A equals P to ERT. So the amount we'll have is equal to the 8,000 times e to the 0.05 times the 6 years. Grabbing my calculator, I find that that amount is $10,798.87 that would be in the account at the end of 6 years.